This is video 3.4 for geometry. Today we're going to be talking about perpendicular lines. We've done a lot of work with parallel lines, but I want to make sure that you have just as much practice with perpendicular lines. So the theorems that you're going to need to write down for today and a couple of definitions is the first one is a perpendicular bisector. We've talked about angle bisectors and we've talked about dividing a line in half at the midpoint. But a perpendicular bisector is going to be a segment that comes in perpendicular to a line that's at that segment's midpoint. So if we were to draw a picture, if we have this segment, say A to B, and we know the midpoint is right here at C, if we have a line that comes down, oh, that's not a very good one. If we have a line that comes down, a line segment, and it intersects AB at the midpoint, so that this is congruent to this, and this forms a 90-degree angle, then we would say that this little line segment is a perpendicular bisector. So it's going to cut the big line into halves. Now, anytime you have a point that is next to a line, so say we have this line and we have this random point up here, the shortest segment that you can draw from that line to or from that point to the line is going to be a perpendicular segment. So the shortest line that you can draw will be this one right here where it's perpendicular. You could draw a line to any point along the line, but the shortest one will be the perpendicular segment. So the shortest distance between 2 points is going to be the perpendicular segment. Now here's your theorem. So if you have two intersecting lines, if you have two intersecting lines and they form a linear pair with congruent angles. So let's say we had, so you have two lines and they intersect. This linear pair that's right here and right here, if those angles are congruent, if this angle is congruent to that one, then the lines are perpendicular. So if you had two intersecting lines like this, and you have a linear pair, this angle is much smaller than this angle, therefore they're not congruent angles. We wouldn't say that this set of intersecting lines is perpendicular. So your intersecting lines are only perpendicular if the angles that they form are congruent. That is theorem 341. The next one is that if you have a plane, this is the perpendicular transversal theorem. So if you have a plane and you have a transversal that is perpendicular to one of two parallel lines. So let's say in a plane we have two parallel lines and we have a transverse that's coming in and it's crossing, and we know that this part right here is perpendicular. So it's perpendicular to the first line, then it has to be perpendicular to the other line. You can prove that using corresponding angles, because corresponding angles have to be congruent. So if that's 90 degrees, that means that has to be 90 degrees. So the second line is also perpendicular. If you have two coplanar lines that are perpendicular to the same line, then the two lines are parallel. So let's say we have this line, and we have a transversal coming down, and we're like, this one is perpendicular and this one's perpendicular. Then that means that this line, let's call this L and let's call this M, that means that L is parallel to M. If they're perpendicular to the same line, then they are parallel to one another. All right, so let's practice a few things. So the distance from a point to a line, so I want you to name the shortest segment from P, this is the point P, to the line AC. What's the shortest segment? Is it PA? Segment PA? No. Is it segment PC? No. Is it segment PB? We can tell that for sure if we know that this is a right angle, then for sure PB is the shortest segment from P to AC, because the shortest distance from a point to a line is going to be the segment that intersects it perpendicularly. All right, so we're going to prove a couple of properties of lines. So we have line AD and line BC, and we're saying that they are parallel, so we know this is parallel to this. And we have AD is perpendicular to AB, so this is a 90-degree angle right there. BC is perpendicular to CD, so this is a 90-degree right there. So we're going to prove that AB is parallel to DC. So to do that, the first thing I'm going to write in is a couple of my given statements. I'm going to say that line AD is parallel to line BC. And then what I'm going to go ahead and use is this BC is perpendicular to DC. So BC is perpendicular to DC. And that is given. So my next statement I'm going to do is I'm going to take my, I don't know why I'm going to use my perpendicular or transversal theorem that says if a transverse is perpendicular to one of two parallel lines, then it's perpendicular to the other. So I have DC that is perpendicular to BC. That means that DC has to be perpendicular to AD. So if this is perpendicular to BC, BC and AB are AD are parallel, so DC has to be perpendicular to AD, and we would say that this is the perpendicular transverse theorem. All right, my next step, I'm going to take this part of my given. So I have my AD is perpendicular to AB. What I'm trying to prove is that AB is parallel to DC. So if AD is perpendicular to DC, this is given. If AD is perpendicular to AB and AD is perpendicular to DC, which is what these two lines say, then I can take those and I can say that AB is parallel to DC because of the two lines that are being perpendicular. So it says if two lines are perpendicular to the same line, then they are parallel lines. That was the previous theorem that we used. So it doesn't really have a name. It'd be helpful if it has a name, but we would just say two lines perpendicular to the same line. We'll just say same line. Then the two lines are parallel. So because AD is perpendicular to AB and AD is perpendicular to DC, then we can say that AB and DC are parallel because two lines that are perpendicular to the same line are parallel lines. All right, that's it for tonight. Definitely less than 10 minutes. We'll do a little bit more practice with this. I just wanted to make sure that you had heard of these theorems before we moved on. So you have a good evening, and I'll see you later.